Sorry, I've been quiet recently. I've actually just come back from a wedding in Kazakhstan of a good friend of mine, Aldar. And so, congratulations to Aldar and Rafina, the new bride and groom. Let's dive into a problem which comes from the Kazakhstan Olympiad paper. We have x to the 5 plus 31 equals y squared. That equation we want to show has no integer solution, so that there are no integers x and y that satisfy this equation. Let's dive into a solution here. The first thing we're going to do is investigate whether x has to be odd or even. And it turns out it can't be even. If x was even, then hopefully it's pretty clear to see that x to the 5 would be a multiple of 4. In fact, it would be a multiple of 32. But in particular, it's a multiple of 4. So this would have to be 0 mod 4. And 31, that's always going to be 3 mod 4. So we'd have 0 plus 3, and that would be 3 mod 4. The only issue with that is y squared, a square number, that can only ever be 0 or 1 mod 4. And so we get a contradiction. And so therefore x cannot be even, and so therefore the only way this is possibly true is if x is odd. Okay, cool. X is odd. Where do we go from here? Well, 31 here, and we've got something to the power of 5. 31 is suspiciously close to 32, which is a power of 5. So let's add 1 to both sides. So we get x to the 5 plus 32 equals y squared plus 1. Now, the great thing about the left-hand side is now we know we can factorize it, because if I substitute x is minus 2 into the left-hand side, I'm going to get minus 2 to the power of 5, which is minus 32, plus 32 is 0. So that means x plus 2 must be a factor. Okay, now you can do long division here. So in fact, I might just do this on the side here. X to the 5 plus 32, I want to divide that by x plus 2. And so I'm going to get x to the 4 first, and x to the 4 it's going to give me x to the 5 plus 2x to the 4. Subtract those from one another, so I get minus 2x to the 4 plus 32. Minus 2x to the 4, so that's going to be minus 2x cubed up there. And so I'm going to get minus 2x to the 4, and then minus 4x cubed. So subtracting those gives me 4x cubed plus 32. So up here I'm going to get plus 4x squared. So 4x cubed then plus 8x squared is going to give me minus 8x squared plus 32. So it's going to give me a minus 8x there, and then bringing that here gives me minus 8x squared minus 16x, and then subtracting those gives me 16x plus 32, so plus 16 there, and then 16x plus 2, 16 times x plus 2 gives me 16x plus 32, and those will cancel. Great, so this thing here, x to the 5 plus 32 is simply x to plus 2 times x to the 4 minus 2x cubed plus 4x squared minus 8x plus 16, and this equals y squared plus 1. Okay, this is all good and well. Now, where do we go from here? We're going to use a fact from number theory, and in particular, an area of number theory known as quadratic residues. So I'm not going to go into too much detail here. So if you've not seen this before, I encourage you to look up quadratic residues from number theory. But this right-hand side here is y squared plus 1, so it's one more than a square number. And so therefore, this guy, this number, y squared plus 1, it cannot have any prime factors that are congruent to 3 mod 4. And so this is a pretty famous result from number theory, as I say. Go ahead and revise this or research this if you've not seen this before. And so now what we're going to do to arrive at a contradiction is show that this left-hand side must contain a prime factor that's congruent to 3 mod 4, and we're going to get our contradiction. Let's have a look at this big thing here. We're going to look at this guy mod 4. What does it give us? Well, x to the 4 is x to the 4, minus 2x cubed is minus 2x cubed, but all these other guys here, those are clearly multiples of 4. So this thing here is the same as x to the 4 minus 2x cubed. This is all mod 4. Now we can recall the fact that x is an odd number. So any odd number to the power of 4 is always going to be 1 mod 4. And then what about a cube number? Well, that's either going to be positive 1 or minus 1 mod 4. So either equal to 1 or minus 1. Now this is going to be 1 either minus 2 or 1 plus 2. But mod 4, either way, that's just going to be 3 mod 4. And so this guy here is going to be 3 mod 4. But this is a contradiction, because if it's 3 mod 4, because it's odd, and it's not too difficult to check that it's odd, because this guy here is well, because up here x is odd. So if I x to the 5 will be odd. If I add 32 to it, it will still be odd. So both of these prime factors must be odd. So this guy here is odd, and if it has three, if it's congruent to 3 mod 4, its prime factors cannot all be 1. Because if they were all 1, then this thing here would multiply and be 1 mod 4. But it's 3 mod 4, which means it has to have at least one prime factor, or in particular, an odd number of prime factors, which are 3 mod 4. But this contradicts this guy. Hence, we have no integer solutions to this equation. A really interesting problem with maybe a strategy of solving which you've not seen before. So hopefully introducing some new techniques there. So hopefully you have enjoyed that. So problem from Kazakhstan, a really beautiful city. I went to Almaty, a really, really beautiful city in a wonderful country. So I'd highly recommend visiting if you've never been before. That's all for today. I'll catch you in the next one. Have a great day.